So our next speaker is, I think she's not ready yet, I think. Let me see.
Oh, I'm ready. I'm ready.
Okay, great. So you made it. So can you share your screen?
Yes.
Okay, please.
Okay, 1 second. Okay, so good afternoon, everyone. Actually, it's 5 o'clock in the morning here, so I should also say good morning. I'm Jin Yang from MIT Kavli Institute. So I'm here to talk about the silicon K gas to dust optical depths towards the galactic bulge. So when we get the data from the X batteries, for example, neutron star batteries, we also want to know what the interstellar medium are contributing to the data. So therefore, we measure the silicon X-ray absorption towards these bright sources in the galactic bulge. Because the dust contained in interstellar matter plays an important role in the composition and evolution of the interstellar medium. So this can tell us the cooling and heating process, help us to understand the star formation. The gas and dust content with silicon in interstellar medium with Chandra high energy transmission grating spectrometer can tell us a lot of information. So we measure the silicon gas to dust optical depths towards 9 bright low mass X-ray batteries, these light sources. And later we compare them to the molecular hydrogen in radium. This shows this background is the Wisconsin H-alpha mapper survey, and this sources shows different direction we are looking at in order to measure the silicon gas and dust optical depths. So these are the sources in our survey. So we use Chandra HETG grating data. They are well calibrated, so power up free, which is specifically designed to measure the silicon edge. So with this highest resolution from Chandra, here are 2 examples in our survey. On the right, the spectrum shows for the GX5-1 with lighting 2.6 kiloseconds exposure time. So this is the silicon gas edge. This is silicon K dust edge. So we can say this source is mainly dust dominated, and only neutral gas contribute to the edge. On the left, it is a spectrum for the GX3+1 with about 200 kiloseconds exposure time. And both gas and dust contribute to the silicon edge. So for all the sources in our survey, we used the fitting for the broadband, we use the broadband continuum models. For the laser band, we've used the silicon gas edge model, dust edge, and the iodized silicon models. So here is an overall view of the fitting for the sources in our survey, then in different locations of the galactic bulge. So I just showed you GX5-1, so this is GX3+1. So from these sources, we can get the gas edge optical depths, as well as the total edge optical depths, including gas plus dust. So for each source, you can say for most of the sources, they are consistent with the MRN standard dust size distribution. On the right figure, so I put the optical depths as a function of the hydrogen column density. So the red dots are the gas optical depths, and the blue are the dust optical depths. You can say for the gas optical depths, they are linearly correlate with hydrogen column density, but for the dust optical, they are not. So this blue dotted curve can be expressed in this formula. So this result tells us the silicon gas is fairly homogeneous in different directions, and the dust, they are not. So we can use this to calculate the dust green columns. So here it's still the same data set. We only plot the dust optical depths. So with this, we can, which means we can, from different direction, we can calculate the dust green columns based on different dust size. So at the end, we compare our results with the latest 21 centimeter radio survey for the carbon oxygen H2 case for 10 kilometers per second. On the left, the background is a radio survey, and this shows the location of each source in our current silicon survey. And on the right, we plot the optical depths as a function of the molecular hydrogen in radio. The red is a silicon gas optical depths, and the blue are still the dust optical depths. So the x-axis is molecular hydrogen in radio. And we can still say the optical depths show, gas optical depths shows show they are linearly dependent on the molecular hydrogen. But for the dust, it shows the self-shielding, so which can expressed in this formula. So finally, we have measured silicon X-ray absorption towards bright sources in different lines of sight in the galactic bulge. And we measure the gas and the optical depths and the silicon, specifically silicon K. For the gas optical depths, they grow fairly consistent with the hydrogen column density. But for the dust optical depths, they are not homogeneous. So we can use this to calculate the dust grain size towards different direction in the galactic bulge. And also our dust optical depths extracted are consistent with standard dust size distribution. And when we compare our results with our radio survey, we found that at the lower amounts of hydrogen, molecular hydrogen, the dust optical depths are also lower. But in the direction of the higher amounts of molecular hydrogen, the dust optical depths are also high. And but for the gas optical depths, they are linearly correlating with molecular hydrogen. Okay, thank you very much. I would like to take the questions.
Okay, thank you for really nice talk, given especially 5 o'clock in the morning.
Thank you. So,
Let's see, any questions? So I will ask one question. So for the bright sources towards this galactic bulge, do you know the rough range, the range of distances? I mean, are they, so you, along the line of sight, you are seeing these sources at, do you have information on the distance?
oh yeah, that's a great question. This can help us actually to measure the distance. Because at a different direction, we already have the molecular hydrogen value in the radio, and since from different direction, we can get the content. Then this can help us to calculate distance. Actually,
Okay.
thank you.
Yeah. Any other question? Okay. Okay, if not, we thank the speaker again. And I think that will conclude our session. And so any other announcements from LOC?
No, thank you.
Okay, if